You know when you're scrolling through an app and it just stutters for a second while loading a massive list? Well, let's dive into this explainer and completely demystify the inner workings of data structures. If you've ever been curious about how your computer actually organizes the mountains of information it handles every single day, you are absolutely in the right place. Today, we're going to translate all that theoretical code into real-world, everyday scenarios and trace exactly how data storage has evolved over time. So here is our roadmap for today. First, we'll outline the core data storage problem. Then we'll check out arrays, look at array insertion and shifting, explore singly linked lists, deal with the tail removal trap, and finally wrap up with doubly linked two-way streets. Let's jump right into section 1, the data storage problem. Before we even look at a single line of code, we really need to understand the fundamental dilemma it was created to solve. Our main job as programmers is basically figuring out the absolute most efficient way to organize, add, and remove data. Early data storage was a lot like the beads on an abacus. It relied on a sequence collection where everything had a strictly fixed physical position. I mean, you can't just magically teleport a red bead right between two green ones, right? The wire itself dictates the physical order. And you know, computer memory originally functioned the exact same way. If you wanted data in the third spot, it physically had to sit in the third spot. Which brings us to section 2, arrays, or as I like to call them, the rigid scoreboard. The array is an absolute classic in computer science. It's brilliant for keeping things in a highly predictable numerical order. Picture your favorite arcade game. The top 10 high scores are tracked in a specific numbered list. Number 1 is always the highest, number 2 is next, and so on. In code, the scoreboard creates exactly 10 permanent slots in the computer's memory, just like permanent painted numbers on an old-school arcade cabinet. Every single player's score is tracked in a very specific, strictly numbered slot. But here's the catch with arrays. You have to think of an array exactly like a tightly packed, physical bookshelf built with solid wood cubbies. Once that bookshelf is built, its capacity cannot grow. In Java, this maximum unchangeable number of items is tracked using something called a dot length. So if your code specifies a length of 10, the computer builds 10 cubbies. If an 11th player somehow miraculously gets a high score, you literally have to tear down the entire wooden bookshelf, build a completely new one with 11 cubbies, and painstakingly move every single item over. As you can guess, that is incredibly inefficient. And that leads us to section 3, array insertion and shifting. So the crucial point here is what actually happens when our rigid bookshelf is nearly full and we need to squeeze a brand new box right into the exact middle. Looking at the underlying logic for adding entries, it's far from simple. Imagine being a librarian. Someone hands you a book that belongs exactly in the dead center of a tightly packed shelf. You physically have to pull out the book at the very end, move it to a new shelf, then slide the next one over and the next one over and over, just to make a gap. That exhausting process is exactly what the for loop in this code is forcing your computer to do. If you have a million scores and a new player grabs second place, you have to move 999,998 records down by one slot. It's an unbelievably heavy lift for the system. Seeing that massive performance bottleneck leads us to a pretty fascinating question. What if we could just link our data together dynamically instead of shifting all these heavy boxes around every time we update a list? Let's move on to our next evolutionary step, which completely bypasses the need to shove data around. Welcome to section 4, singly linked lists, basically the ultimate scavenger hunt. Unlike the rigid array bookshelf where every item desperately needs its own consecutive cubby, a singly linked list lets you operate totally differently. Imagine just throwing items haphazardly into a massive warehouse. It honestly doesn't matter where they land, as long as each item has a sticky note explicitly telling you where to find the next one. Because each piece of data tells you where the subsequent piece is hiding, there's absolutely zero element shifting required. The secret ingredient making all this work is the node. It functions exactly like a clue in a real-world scavenger hunt. Think about it. In a scavenger hunt, you find a physical box. Inside is your prize. That's your actual data. But at the bottom of the box is a piece of paper with an address on it, and that is your pointer. You don't hold a master map to the whole entire course. You just have your current node pointing strictly to the location of the very next one. Because we're literally just following clues, adding a new starting point to our scavenger hunt is blazingly fast. To add a new start, we just hand out a new clue to our players. We write down the location of the old starting point on it and tell everyone, hey, start here instead. The computer memory updates instantly. No shifting a million records down the line. Boom, done. And it's so cool how the theoretical concept perfectly matches the Java programming.
To insert the airport code LAX to the front of our flight path, the add first logic simply creates a new node for LAX, sets its pointer to the old head, which was MSP, and magically updates the official starting line. Theory and code just working together in perfect harmony.
But wait, there is a catch. Section 5, the tail removal trap. When a tail node points to a null value, it means the scavenger hunt is officially over. But if we decide we want to remove that final destination, the very end of our list, we run into a huge problem. You see, our clue network only points forward. It's a strict one-way street. LAX points to MSP, which points to ATL, which points to BOS. You can never go in reverse. Think about it for a second. If you delete that final tail node, the second to last node still thinks the tail exists. It's pointing straight to a dead end. And if you can't step backward from the tail to update that previous node's pointer to null, how do you fix the list? Well, you are forced to start at the very beginning and walk through the entire scavenger hunt all over again just to find that second to last clue. Imagine running across an entire city following a million clues just to tell the guy at clue number 999,999 to throw his instruction card away. That is a massive, massive waste of processing power. So how do we fix it? Section 6. Doubly linked lists, or two-way streets. The solution here is amazingly simple, but incredibly powerful. By paying just a little extra memory cost to add a previous link to every single node, we completely transform our scavenger hunt into a two-way street. A doubly linked list works exactly like the back and forward buttons on your web browser. You can navigate the sequence smoothly in either direction. It's a total game changer. By adding literally just one single line of code, a prev reference right under the next reference, we unlock the power to jump backwards seamlessly. Now, if you want to delete the tail node, you just look at its prev pointer, tell that second to last node to point to null, and you are done. It's instant deletion without having to run across the city from the start. Now, to make these two-way digital streets even safer, developers use something called sentinels. Think of these sentinel nodes as the impenetrable, concrete dead ends at the very edges of our road. They don't actually hold any real data at all. They're essentially just dummy header and trailer nodes. Without sentinels, a program that's trying to search backward might accidentally look right past the absolute beginning of the list, which would instantly crash the entire application. So, sentinels act as the digital guardrails, keeping the code safely on the road. They guarantee we always have a definitive start and endpoint to bump into. We've absolutely covered a ton of ground today, moving from rigid array bookshelves that require a ton of heavy lifting to one-way scavenger hunts, all the way up to sentinel-guarded two-way streets. Hopefully, this explainer has given you the visual blueprint to confidently make your own choices when you're writing code. So the next time you boot up an app and it loads instantly, ask yourself, are you looking at a rigid, perfectly organized array, or are you secretly following the clues of a dynamically linked list? Thanks so much for joining me on this explainer. I'll catch you next time.